G'day chemistry students. In our previous video, we were looking at this new value Keq, our way of being able to quantitatively express and apply equilibrium concepts. So in that first video, our main focus was being able to write up equilibrium expressions. We're now going to be using those expressions in this video to complete some simple Keq calculations. Let's get into it. So the main point of this video is to go through a few different practice questions, which will get you to apply some of these quantitative concepts in slightly different ways. But in each of these calculations, I'm going to be following 4 general steps. So the first step that I'm going to be doing in each of these solutions is trying to identify the balanced chemical equation. Usually for these kind of questions, you get the equation given to you. Technically though, you could be required to write up your own balance equation, but that's not really something that happens within the scope of this topic. What we then need to do is write up an equilibrium expression for that equation. We then need to either identify the concentrations of all of the chemicals that are in the equilibrium, so they would just be given to you. More likely though, you're going to be asked to determine the concentrations, and there's a few different ways that that can be done. That's part of the reason why I'll be showing you a few different practice questions that get you to solve the problem in slightly different ways. Once you know all the concentrations, you can substitute all of them into the equilibrium expression. You then plug it into your calculator and you end up with a Keq value at the end, an equilibrium constant. So let's get into these calculations. So for this first question, what we have is a mixture of gases, methane, water, carbon monoxide, and hydrogen gas. And they're inside a closed vessel, which means that they can form equilibrium because we're not going to be losing or gaining any reactants or products. And the vessel is 5 liters. And so we're told what that equilibrium is between the methane and the water forming carbon monoxide and hydrogen gas, and then the reverse reaction also being present. What we're being told is to assume that the mixture is at equilibrium and to calculate the equilibrium constant Keq at 1003 degrees Kelvin. So first off, I just want to highlight that temperatures have been quoted a couple of times in this question. I will talk about this in a little bit more detail in the next video, but we already know that Le Chatelier's principle says that if there is a temperature change, you're going to end up changing the concentrations of your products and reactants. So you'll see a lot of the time that within these questions where we're calculating Keq, the question will tell you that the temperature is exactly the same and the temperature is constant. And the reason for that is because technically, if there were temperature changes happening within the system, what that can mean is that concentrations change, and that means that when you start calculating Keq with the concentrations that you find, if they're changing all the time, then the Keq is not going to remain constant either. So you will see that those temperatures are quoted, and that's generally just to show that the temperature is the same and that we don't have to worry about temperature changes at all. In fact, we don't calculate the effect of temperature change on Keq, we just talk about it qualitatively, but I'll expand on that in the next video. What I want to show as well is a quick reminder that Celsius and Kelvin are related to each other. So these temperatures are actually the same. 730 plus 273 is 1003 Kelvin. So that's all completely fine. Those temperatures are exactly the same despite them being in different units. The next thing that I want to emphasize is our steps. So what we need to be doing first is identifying the balanced chemical equation to solve this problem. That's there. So we can be using those chemicals and their molar ratios and all that sort of stuff to, in a moment, write up an equilibrium expression. So I'll do that in a second. What we also need to do is determine the concentrations of all chemicals when at equilibrium. So we've been told that the mixture that we've been told about is at equilibrium already. We know what the reaction vessel volume is, and we also know N, the quantity of all of these substances. So we're going to be able to use this information to solve our problem. So, seeing as we have our balanced chemical equation already set up, what we want to be doing first is writing up the equilibrium expression for this reaction. So to do that, that's product of products divided by product of reactants. So I'm going to start with the concentration of the carbon monoxide times the concentration of the hydrogen gas. We're going to raise that to the power of 3 to match the coefficient that's there, and divide by the concentration of the methane and the concentration of the water. Just note that the concentration of the water is included in this one because the water is a gas, so it has a concentration unlike a liquid version. The next thing that we need to do is step 3, determine the concentrations of all chemicals when at equilibrium. I think the biggest pitfall for a question like this is assuming that the data up here about the quantity in moles is the actual concentration. We should know though that if something is written as N, that is the number of moles. The relationship between C and N is C equals N over V. We also have V here, the vessel is 5 litres. So what we need to do next is maybe just come up with a little column on the side and calculate all of those concentrations. So I'm just taking the number of moles and dividing it by 5 litres. I'm just going to put those in my calculator, make sure that I get them correct and write them next to those values. So the last thing that we need to do is substitute the equilibrium concentrations. They're all here. We also have the equilibrium expression to be able to substitute into. So we're going to do that now. So Keq is equal to the concentration of carbon monoxide, 0.75, times the concentration of the hydrogen, which is 0.75, and we're going to cube that. Divide all of that by the concentration of methane, 0.4, times the concentration of water, 0.25. So putting all of that into a calculator, we should end up with our answer. And that comes to be 4.21875. To give the best answer, we should probably be giving this to 2 significant figures. So that matches our volumes and these quantities in moles over here. So that would be rounded to 4.2. Note as well that there are no units for Keq, we just give it as a standard number. So in this question, what's going to be a little bit different is we have not been given all of the equilibrium concentrations, or we're not able to find all of the equilibrium concentrations with the data that we've been given. What we actually need to look at is how the concentrations of our reactants and products are changing from the beginning of the process to the end when equilibrium is reached. So what we want to do first is identify a balanced chemical equation, and that's the reaction between hydrogen iodide and its products iodine gas and hydrogen gas. We then also want to write up an equilibrium expression, which I'm going to do right away. So product of products means that we've got concentration of I2 times the concentration of H2, and that's being divided by the product of our reactants, so that's the concentration of hydrogen iodide, and we're going to be squaring that. And this is where the question gets a little bit different now, because what we now need to do is determine the concentration of all of those chemicals at equilibrium, and that's based on some of the information that we have been given in the question itself. So what we're told is the initial concentration of hydrogen iodide, as well as the equilibrium concentration of the hydrogen. Now, it doesn't look like we've been given a lot of information. It seems like we've only been given the concentration of the hydrogen and nothing else. But we've actually been given enough information to be able to do a full calculation from here. So to be able to do step number 3 to determine the concentration of all chemicals at equilibrium, we need to draw up this thing called an ice table, which I've started to do here. And what the ice table will do will track the concentrations from the beginning of when the system was formed to the end when it reaches equilibrium. So with the information that we've been given, what we have been told is that the initial concentration of hydrogen iodide is 0.75 0.800 moles per liter. Now, we can assume as well that the concentrations of the products are going to be 0 at the beginning, as we have not been told anything else about them. What we've also been told is the equilibrium concentrations for the hydrogen in particular. So what that means is we know that when this system reaches equilibrium, the hydrogen concentration is 0.0884. So we've got that there. And what that means is that the hydrogen concentration has changed as an increase of 0.884 moles per liter. It's gone from 0 and jumped up to that number. What we can also assume is that the iodine concentration is going to increase by the same amount, and that's due to the molar ratios in the reaction equation. So if the hydrogen concentration has increased by 0.884 moles per liter, then that should be the same for the iodine as well. And so that means that its end resultant concentration at equilibrium is going to be the same as well. So then the question becomes, what has happened to that hydrogen iodide? I'm hoping that we can assume that the hydrogen iodide is being consumed to form hydrogen and iodine gas. So what we're expecting is a negative change for sure. But because of the molar ratios here, which are 2 to 1 to 1, what needs to happen is that double the amount of hydrogen iodide needs to be consumed to produce the correct amount of hydrogen or the correct amount of iodine. So it's not just going to lose 0.0884 moles per liter of concentration, but it's going to lose 2 times that, and that is because of our molar ratios. So doing the math really quickly, 0.800 minus 0.1768 is equal to 0.6232 moles per liter. So with this information down the bottom, we have all of our equilibrium concentrations, and they can be substituted into our equilibrium expression. So Keq is going to be equal to 0.884 times 0.884, that's for our hydrogen and iodine concentrations, divided by 0.6232 squared. And that's equal to 2.0121. Looking at our significant figures, we should be reporting this to 3 significant figures. So the 3 significant figures here and here. So that would be 2.01 would be our Keq value. So this final question that I have for you is slightly different to the other two, but is still related to this Keq concept. And it builds on the question that I did at the end of the previous video. In this one, we have 2 reaction equations. We have hydrogen iodide forming hydrogen and iodine gas, the same one that we just did for the previous question. But we also have the same reaction with the same products and reactants. However, the coefficients are different for these. Every coefficient has been halved in size. And so this actually has an impact on the resultant Keq. Now, we don't have to substitute numbers and concentrations in for all of these to know what that value is going to be. If we already know that the Keq for this first reaction is 0.0201, which is here, we calculated that already. If we were to change the coefficients here mathematically, what that means is we would be taking our Keq and we'd be taking our original Keq for the original reaction and raising it to the power of a half. So what you'll see is that for each of these spots here, in the resultant equilibrium expression, what happens is that the indexes drop by a half. And so as a result, overall, you can do a calculation where you raise the original Keq value to a half. So for those that are a little bit more mathematically minded and remember all their index rules and stuff like that, really what that means that we're doing is taking KEQ, and if you're raising something to the half, you're just square rooting it. The answer would be the square root of 0.0201, and that is 0.142. On the flip side of this, if we were to look at this reaction here and instead double all of the coefficients, so we had 4HI in equilibrium with 2H2 and 2I2, we would end up having an equilibrium expression that looks like this. And the KEQ would be equal to our original KEQ, but squared. And so that would be 0.0201 squared, and that is 4.04 times 10 to the negative 4. So there you go, a bunch of KEQ calculations. Thank you very much, everyone. Hopefully you've got a little bit of a better idea of how to calculate KEQ when you're given some data. What we're going to be doing in the next lesson is applying these KEQ values. So looking at the value of the KEQ and trying to extract any information that we can. We're also going to be comparing KEQ to experimental data to determine whether or not a system is in equilibrium. And we're also going to talk about how temperature is able to affect the equilibrium constant as well in a bit more detail. But until then, have a good one.